Welcome to the deep dive. Today we're jumping into something pretty neat in the AI world, knowledge distillation. Uh, Basically, it's about making those big, powerful AI models smaller and faster, right? Without losing too much of what makes them smart.
Exactly. It's all about efficiency. We're
Uh,
exploring how you take these super complex AI brains and shrink them down so they can run on, less powerful hardware, run faster, but still keep most of their smarts.
okay. And we're using the document knowledge distillation v2.pdf as our guide today. It looks pretty comprehensive.
It is, yeah. It covers a lot of ground.
So our mission really is to unpack why this is important, how it actually works, this whole teacher-student thing, and where it's making a difference out there, a shortcut to understanding AI efficiency, if you will.
Sounds good. Let's dive in.
Right. So first things first, why should we even care about knowledge distillation? What's the big deal?
Well, the main reason, it really boils down to deployment. Getting these AI models out into the real world. A lot of the best ones are just huge. They need tons of computing power.
Right. They live in data centers mostly.
Pretty much. So knowledge distillation is the key to getting that same kind of intelligence onto devices that don't have those kinds of resources.
Like what kind of devices? Can you give some examples? Where does this really matter day to day?
Think about your smartphone. All the AI stuff happening right there, like real-time computer vision, maybe identifying things in your camera feed,
Yeah.
or AR features.
Yeah, that needs to be instant.
Exactly.
Yeah.
And it can't kill your battery. Distillation lets developers compress those complex vision models so they run smoothly right on the phone. It's about bringing AI to your fingertips, basically.
Okay, that makes sense. AI without needing a supercomputer in your pocket. What about other areas beyond phones?
No, definitely. Think about the Internet of Things, IoT devices. You've got all these little sensors out there collecting data.
Right, in smart homes, factories, cities.
Yeah, everywhere. Knowledge distillation lets us put smarter AI right onto those low-power devices so they can analyze data right there at the edge instead of sending everything back to the cloud.
Which is faster, right? And probably better for privacy sometime.
Much faster, saves bandwidth, and, yeah, potentially better for privacy, too. The core idea is putting the intelligence right where the data is actually being generated.
I see. So it's like fitting a big brain into a small package. But it's not just size, is it? Speed must be critical, too.
Oh, absolutely. Smaller models just run faster. Their inference time, the time it takes to make a prediction, is much lower.
Makes sense. Fewer calculations.
Exactly. And they use less memory. That leads to a whole cascade of benefits. It's cheaper to run these AI systems. You can handle more users with the same hardware. It just makes deploying AI much, much easier overall.
And I guess there's an environmental angle, too. Less computing means less energy.
That's a really important point, yeah. Reducing computational needs directly improves energy efficiency. So low running costs, yes, but also a smaller carbon footprint. It helps make AI more sustainable, potentially even letting older hardware stay useful for longer.
Okay, smaller, faster, cheaper, greener. That's a compelling pitch. So how does this magic actually happen? You mentioned a teacher and a student.
Right, that's the core analogy, the teacher-student paradigm. You start with a teacher model.
Yeah.
That's usually a big, complex neural network. It's been trained extensively, maybe on a huge data set, and it performs really well. It's the expert.
The gold standard.
Kinda, yeah. Then you have the student model. This one is designed from the ground up to be smaller, simpler, fewer layers, maybe fewer connections, just more streamlined.
The apprentice learning the ropes.
Exactly that. The whole point is to train this smaller student model to mimic the teacher. Not just to get the same answers, but to capture the knowledge the teacher has learned.
Okay, so what makes the teacher suited to be a teacher and the student suited to be a student? What are their defining traits?
The teacher, because it's large and complex, has a huge capacity to learn subtle patterns, really intricate details in the data. The student, though, is built for efficiency. Speed, low memory usage, those are its priorities. Its architecture might be specifically chosen for, say, a mobile chip.
And what does the student gain from this mentorship? Besides being smaller, obviously.
Well, surprisingly, the student often ends up more accurate than if you just trained that same small architecture directly on the data from scratch.
Really? How does that work?
By learning from the teacher's insights, it gets a kind of head start. It can become more robust, better at handling noisy data, and it often generalizes better to new examples it hasn't seen before. Sometimes it might even need less raw data to train effectively because it's learning this distilled knowledge.
That's cool. It's like getting wisdom passed down, not just facts. Now,
Yeah.
you said the student learns the teacher's knowledge. How is that different from just learning the right answers, the labels?
Ah, that's the crucial part. It's about how the knowledge is transferred. And the key concept here is soft targets. Normally, when we train AI, we use hard labels. Like this picture is a dog, 100% dog, 0% everything else.
Or the one hot encoding.
Exactly.
Yeah.
But a well-trained teacher model doesn't just output dog, it outputs probabilities for all the classes it knows. So it might say 95% dog, but maybe 3% cat, 1% wolf, and tiny probabilities for everything else.
Okay.
Those small probabilities for the wrong answers, that's the dark knowledge. It tells you something about how the teacher sees the world. It thinks this image is very dog-like, but it has some tiny resemblance to a cat or a wolf, much more so than, say, a bicycle.
Ah, I see. So the teacher's hesitation or its pattern of confusion actually contains useful information about how different classes relate to each other.
Precisely. The teacher's mistakes, or near mistakes, are informative, and we want the student to learn these nuances.
How do we get the student to pick up on those subtle hints?
That's where temperature scaling comes in. It's a parameter, usually called T, that we apply within the softmax function. That's the function that turns the model's internal scores into probabilities.
Okay.
If you set the temperature T higher than 1, it softens the probability distribution. It makes the probabilities less peaky, more spread out. This effectively amplifies those smaller probabilities, making the dark knowledge more visible.
So turning up the heat reveals the teacher's subtle thinking.
Kind of, yeah. A low temperature, like T1, which is standard softmax, gives you sharper probabilities. A high temperature smooths things out, revealing the teacher's uncertainty and its sense of similarity between classes.
Can you give a quick example, like with some numbers?
Sure. Let's say the teacher's internal scores, the logits for 3 classes are 2.0, 1.0, 0.1. Pretty confident about the first class.
Right.
With standard softmax, T1, the probabilities might be something like 0.66, 0.24, 0.10. Clear winner.
Okay.
Now, crank up the temperature to, say, T5. Apply softmax again. The probabilities might become much flatter, maybe 0.42, 0.31, 0.28.
Whoa, yeah, much closer together.
See, the relative probabilities of the second and third classes have increased compared to the first. The student can now learn that while the first class is the most likely, the teacher also sees some connection to the others. It's learning a richer signal than just class 1 is right. It's learning about the relationships.
That's a really clear way to put it. It's learning the teacher's confidence landscape, not just the peak. So how do we mathematically encourage the student to match this softened landscape?
We use a specific type of loss function. One of the most common is the Kullback-Leibler divergence, or KL divergence.
KL divergence. Okay, what does that do?
It measures the difference, or the distance, between two probability distributions. In our case, we use it to measure how different the student's softened probability output, using the same high temperature T, is from the teacher's softened probability output.
So it's like a penalty for the student disagreeing with the teacher's softened view.
Essentially, yes. We want to minimize this KL divergence. The closer the student's distribution gets to the teacher's, the lower the KL divergence value. The goal is to make the student's probabilistic reasoning aligned with the teacher's.
Got it. Minimize the mismatch. Is that the only thing the student is trying to minimize? Does it still learn the actual right answers?
Good question. Usually, no, it's not the only loss. We typically combine the KL divergence loss, calculated using the soft targets from the teacher and the soft predictions from the student, both at high temperature T, with a standard cross-entropy loss.
Ah, the normal loss function.
Right. The cross-entropy loss is calculated using the student's hard predictions at temperature T1 and the actual true hard labels from the data set.
So it's learning two things. Mimic the teacher's nuanced view, and get the ground truth right.
Exactly. It's a balance. You're learning the why from the teacher via KL divergence and the what from the ground truth via cross-entropy.
How do you control that balance? How much weight do you give to each part?
That's handled by a weighting factor, usually called alpha. You have a term like alpha cross-entropy loss plus 1 alpha, KL divergence loss. Alpha is a hyperparameter you tune.
So if alpha is high, it focuses more on the ground truth labels.
Yep. And if alpha is low, it focuses more on matching the teacher's soft targets. Finding the sweet spot, the right alpha, often requires some experimentation, but it's key to getting the best student performance.
Okay, this framework makes a lot of sense now. Teacher, student, soft targets, temperature, KL divergence, plus the standard loss. Seems like a solid recipe. Has this idea been floating around for a while? What's the history?
It has. Well, the specific approach we just discussed, using soft targets and temperature, was really formalized and popularized by Geoffrey Hinton and his colleagues in a 2014-2015 paper.
Ah, the famous Hinton paper.
That's the one. But the underlying idea of model compression, making networks smaller, Goes back further. People were working on it in the late 80s and early 90s.
Really? Like what?
There were techniques like optimal brain damage and optimal brain surgery.
What great names,
Yeah.
right? Huh?
Yeah, very evocative.
They were essentially early forms of network pruning, trying to figure out which connections or weights in a trained network were least important and could be removed without hurting performance too much.
So trimming the fat from the network.
Pretty much. Then, deep learning had its big resurgence, GPUs became powerful, and we started training these massive models in the 2000s and 2010s.
Right, the ImageNet moment and all that.
Exactly. And suddenly, the need for compression became much more acute. We could build these giant, incredibly accurate models, but getting them to run anywhere outside a research lab or data center was a challenge. That really set the stage for Hinton's work.
So necessity being the mother of invention, what was the key insight in that 2014-2015 paper that really kicked things off? It was the clear formulation of using the teacher's full output distribution, the soft targets smoothed by temperature, as the primary training signal for the student. And crucially, showing that this allowed a smaller student model, sometimes with a totally different architecture, to learn much better than if it was just trained on the hard labels alone. It provided a concrete, effective mechanism for transferring that dark knowledge.
And that opened the floodgates for more research.
Absolutely. It sparked a huge amount of work. People started exploring variations and improvements almost immediately.
Like what? How did it evolve from there?
Well, the initial methods, including Hinton's, were mostly what we now call response-based distillation. They focused on matching the final output layer, the logits or probabilities.
Okay.
But then researchers thought, hey, there's probably useful information buried deeper inside the teacher network in the intermediate layers. This led to feature-based distillation.
Feature-based. So looking inside the black box.
Kind of, yeah. Instead of just matching the final answer, the idea is to make the student's internal representations, the patterns of activation in its hidden layers, look similar to the teacher's internal representations for the same input.
How do you even compare those?
There are different ways. An early influential paper, FitNets, used hints from deeper, wider teacher layers to guide the training of shallower, thinner student layers. Other methods try to directly minimize the difference between activation maps at corresponding layers, often using something like mean squared error.
So trying to make the student think like the teacher, layer by layer almost.
That's a good way to put it. And building on that, people started looking at transferring attention patterns, especially with transformers becoming so dominant.
Making the student pay attention to the same things as the teacher.
Exactly. You train the student to align its attention maps with the teacher's attention maps. This not only transfers knowledge, but can also help with interpreting what the student model is focusing on.
That sounds really powerful. What about this self-distillation idea? Does that mean no teachers needed?
Correct. It's a fascinating twist. In self-distillation, a model essentially learns from itself. Techniques like born-again networks or deep mutual learning involve training a model, then using its own softened predictions as targets in a subsequent training phase, or having multiple models teach each other during training.
Wow, okay. The model becomes its own mentor.
Yeah.
So we have response-based, feature-based, self-distillation. Let's circle back to the classics. Hinton's original method will let to gig you actually implement that step by step.
Okay, yeah. First, you need a good teacher model. Train a large, complex network until it performs really well on your task. That's step one.
Got the extart.
Step two, use this trained teacher to process your entire training data set. But instead of just getting the final prediction, you record its output before the final activation, the logits, and then apply the softmax function with a high temperature, T1. These are your soft targets.
So capture the nuanced probability distributions for all the training data.
Right. Step three, train your smaller student model. The key is the loss function. It's a weighted sum, remember. Part one is the KL divergence between the student's logits, also passed through softmax with the same high temperature T, and the teacher's soft targets you just generated.
Okay, match the teacher's soft view.
Part two is the standard cross-entropy loss between the student's normal output, logits through softmax with T1, and the actual ground truth hard labels.
And get the right answer.
Precisely. You train the student by minimizing this combined loss. This approach has worked really well for things like image classification on SciFAR datasets, and importantly, in NLP, it was key to creating models like DistillBERT from the much larger BERT model.
DistillBERT is a great example. Much smaller, much faster, but still really capable. Okay, besides matching logits, what other ways are there to do response-based distillation?
Well, Instead of just matching the logits directly, some methods focus explicitly on aligning the shape of the entire probability distribution. There are also other ways to soften outputs besides temperature scaling. Label smoothing is one technique sometimes mentioned in this context.
Label smoothing, how's that work?
It's actually a regularization technique used even without distillation. Instead of training on perfectly hard labels like 0, 0, 1, 0, you slightly adjust them, maybe to something like 0.025, 0.025, 0.925, 0.925, 0.025. You distribute a tiny bit of probability mass to the incorrect classes.
Ah, okay, so the model doesn't become too confident in its top prediction.
Exactly. It encourages the model to be less certain. While it achieves a kind of softening, it doesn't really capture that rich, data-driven interclass relationship information that you get from a powerful teacher model's actual soft targets. So, related, but different from true distillation.
Gotcha. What about using multiple teachers? Is that a thing? Learning from a committee?
Oh yeah, definitely. Distilling from an ensemble of teacher models is often very effective.
Why? What's the benefit?
If you have several different high-performing teacher models, maybe trained with different initializations or slightly different data, they likely make different kinds of mistakes or have learned slightly different perspectives. By averaging their soft targets, or using them in other ways, the student can learn a more robust and generalized representation that captures the collective wisdom.
Sort of cancels out the individual biases or weaknesses.
That's the idea. The downside, of course, is you have to train and run multiple large teacher models first, which costs time and compute. But the performance boost for the student can be significant.
Makes sense. Okay, let's dive back into feature-based methods. You said matching intermediate activations using mean squared error, for example. What are the tricky parts there?
One big challenge is often dimensionality mismatch. The teacher's layer might produce a feature map with, say, 512 channels, while the corresponding student layer only has 128.
Right, they don't line up.
So you need a way to make them comparable. Maybe you use a small linear layer, like a 1-by-1 convolution, to project the teacher's or student's features into a common dimension before calculating the loss. Or other techniques, like pooling.
Okay, so you need some kind of adapter layer sometimes.
Often, yes. Another consideration is which layers to match. Matching every single layer can be computationally expensive and might not even be optimal. Choosing key layers that represent important stages of processing, maybe guided by domain knowledge or further analysis, is usually better.
And is there a risk of forcing the student to mimic too closely, maybe hindering its own learning?
That's a potential issue, sometimes related to the information bottleneck idea. You want to transfer the useful information, maybe not every single detail of the teacher's computation, allowing the student some flexibility to find its own efficient pathways. It's a balancing act.
Right, and the attention transfer, you mentioned, how do you compare attention maps? Is it similar loss functions?
Yeah, very similar. You can use KL divergence or MSE loss again to minimize the difference between the teacher's attention distribution over the input, or over previous layers, and the student's attention distribution for the same input. The goal is to teach the student where to look.
And that helps with interpretability too, you said.
It can, yeah. If the student learns to attend to similar features as a well-understood teacher, it gives us more confidence in its reasoning. Tools like attention rollout help visualize how attention flows through the layers.
Cool. What about factor transfer with SVD? That sounds complex.
It's definitely more on the mathematical side. SVD, singular value decomposition, is a matrix factorization technique. The idea here is to decompose the teacher's activation maps at certain layers into their core components or factors. Then you transfer only the most significant factors, the ones capturing the most important variations, to the student. It's a way to compress the knowledge being transferred from the feature maps.
A more targeted way of transferring the essence of the features and neuron importance metrics, like saliency mapping.
Right. This is about identifying which individual neurons in the teacher's intermediate layers are most influential for its final predictions. Saliency maps can highlight input regions that strongly activate specific neurons. Once you know which teacher neurons are important, you can specifically encourage the student's corresponding neurons to behave similarly, making the distillation more focused.
Like finding the star players on the teacher team and having the student learn directly from them.
Exactly. It's about targeted knowledge transfer based on importance.
Okay, we've covered a lot of ground on the how. Let's shift to some of the more advanced or newer frontiers. What's happening beyond these core techniques?
Well, self-distillation, as we touched on, is a really active area. The idea that a model can iteratively refine itself is quite powerful and simplifies the pipeline since you don't need a separate pre-trained teacher.
What are the pros and cons there?
The pro is simplicity and sometimes improved performance over baseline training. The con is that it usually takes longer to train than standard training, and the gains might be marginal compared to using a very strong separate teacher.
Makes sense. What about mixing modalities, like vision and language?
Yeah, cross-modal distillation is super interesting, transferring knowledge from, say, a powerful vision model to a language model, or vice versa, or distilling knowledge from a model trained on multiple tasks, multitask learning, into a smaller single-task model, or even a smaller multitask model.
What are the challenges there? The data types are so different.
The modality gap is the big challenge. How do you align representations from images and text? Often it involves finding or learning a shared embedding space where concepts from different modalities can be compared. It's complex, but it holds a lot of promise for more integrated AI.
And relational knowledge, preserving relationships between samples.
Right. Instead of just looking at single input-output pairs, relational distillation tries to ensure that the relationships between different data points in the teacher's representation space are preserved in the student space.
How do you measure that relationship?
Often using distance metrics, like if two images are considered close by the teacher, their feature vectors have a small Euclidean distance or high cosine similarity. The student should also learn to embed them closely. This can help the student generalize better by understanding the underlying structure of the data manifold.
Okay, learning the data's map from the teacher.
Yeah.
What about making models tougher against attacks? Adversarial distillation.
Yeah, that's crucial for security. The idea is to make the student model more robust to adversarial examples, those slightly perturbed inputs designed to fool the model.
How does distillation help?
You can incorporate adversarial training principles. Maybe you generate adversarial examples using the teacher model and then train the student to be resistant to those. Or you can use GANs, generative adversarial networks, where a generator tries to create challenging inputs specifically for the student, making it stronger.
Using adversarial methods during distillation to toughen up the student. Clever. And optimizing those teacher ensembles. You mentioned diversity.
Right. If you're distilling from multiple teachers, it helps if they are diverse, meaning they make different errors or have learned different facets of the problem. Research looks into how to measure this diversity, for example, how much their predictions disagree, and how diversity impacts the student's ability to learn a more general solution. More diversity often leads to a better student.
And are people trying to automate this whole process, make it less fiddly?
Definitely. Meta-learning is being applied to try and learn the optimal distillation strategy itself, like automatically finding the best temperature, alpha, or even which layers to distill from.
Wow, learning how to distill.
Yeah. And techniques from AutoML and Neural Architecture Search, NAS, are being used to automatically design the student architecture, searching for one that's particularly good at absorbing knowledge from a specific teacher.
Taking the human guesswork out of it.
That's the goal. Plus, there are adaptive frameworks emerging, things like curriculum distillation, where you start with easier examples or simpler knowledge from the teacher and gradually increase the complexity. Or online distillation, where the student learns continuously from a teacher that might also be learning or updating over time. It's all about making the process smarter and more efficient.
The field is clearly moving fast. Okay, let's ground this in specifics. Computer vision. How is distillation used there day to day?
It's huge in CV. Compressing big CNNs is a primary use case. You take a ResNet 152 or something powerful and distill it into a mobile net or a custom smaller architecture for mobile deployment.
Using those feature map matching techniques we discussed.
Often, yes. Layer-wise distillation, trying to mimic feature maps with MSE loss, is common, or just matching the final predictions, logits. Training often involves heavy data augmentation, maybe focusing the distillation loss on harder examples where the teacher really excels, or using that curriculum learning idea.
What about tasks like finding objects in an image, object detection?
Yep, crucial there too. Models like Faster RCNN or YOLO have complex outputs, bounding box coordinates, object class probabilities. Distillation helps transfer all that. You can distill the classification part, the regression part for the box coordinates, and even the features from the backbone network.
Are there special challenges for detection or segmentation, where you predict for many locations or pixels?
Yes, these dense prediction tasks add complexity. Aligning features between teacher and student can be tricky if their spatial resolutions differ. Balancing the different loss components, e.g. classification versus localization, is important. Sometimes you need instance-level distillation focusing on each detected object individually, like in mask RCNN for segmentation masks.
And for segmentation itself, like coloring in all the pixels belonging to cars in a street scene.
Similar ideas apply. For models like UNet or DeepLab, you can do pixel-wise distillation, matching the predicted class for each pixel, or region-based distillation, matching average predictions over small areas. It's key for getting accurate segmentation on mobile devices or embedded systems where you can't run the biggest models.
What about generative models, making AI create images or transfer styles? Can you distill those?
You can, but it's harder. GANs, in particular, have tricky training dynamics with their generator and discriminator. But people are doing it. You might distill the generator to make it faster at producing images or distill the discriminator. Sometimes the student discriminator learns from the teacher's assessment of real versus fake images.
What's the goal there usually? Speed or quality?
Often it's about getting a good trade-off. Can we make a smaller GAN that still produces decent quality images, maybe fast enough for real-time applications or edge deployment? Metrics like FID or inception score help measure that trade-off.
Okay, shifting gears to NLP. You mentioned Distilbert. How prevalent is distillation for these big language models?
Extremely prevalent. Models like BERT, GPT, T5 are incredibly powerful but also enormous. Distillation is the main way we get practical, usable versions.
How do they do it? What gets transferred?
Several things. Matching the output probability distribution over the vocabulary is common, but also, crucially, matching the hidden state vectors from intermediate layers. These capture rich contextual information. And transferring the attention patterns, as we discussed, is also very important for transformers. TinyBERT is another example that uses distillation at multiple stages.
Are there techniques specific to certain NLP tasks, like translation?
Yes. For sequence-to-sequence models, like in translation or summarization, you can distill token by token, or try to match the overall sequence probability. Some methods even try to distill the search process, like beam search, that the teacher uses to generate the output. Aligning attention weights between source and target language is also a focus in translation.
What about simpler tasks like classifying text?
For things like sentiment analysis or topic classification, distillation often focuses on transferring knowledge from key layers of the teacher, like the final classification layer or pooled representations, and maybe using aggregation techniques if distilling from multiple layers.
And pre-trained models. Is it better to distill a general-purpose smaller model first or distill directly for a specific task?
Both approaches exist. Task-agnostic distillation creates a smaller foundation model, like Distilbert, which you can then fine-tune. Task-specific distillation trains a student directly to mimic a large teacher fine-tuned for one task. The challenge is always preserving that deep understanding of language context that the huge pre-trained models have.
NLP data has its own quirks, like sentences of different lengths. How does distillation handle that?
Padding and truncation are standard ways to make sequences uniform for batching, and distillation methods need to work with that, perhaps using attention masks to ignore padded tokens. Preserving deeper linguistic features like syntax is an ongoing research area, sometimes involving auxiliary tasks during distillation. An evaluation uses NLP-specific metrics, BLEU, Rouge for generation, F1, accuracy for classification, etc.
Seems like distillation is everywhere. What about speech recognition or even reinforcement learning?
Yep, used there too. In speech, it's used to compress the acoustic models that map audio features to phonetic UNOs, or the full end-to-end systems that go straight from audio to text. Making these models small and fast is critical for on-device speech recognition.
And for generating speech, text-to-speech.
Absolutely. Models like Takatron or WaveNet that generate realistic speech are often very computationally intensive. Distillation is key to shrinking them down while trying to maintain voice quality and naturalness. Google has published work on distilling WaveNet for their assistant, for instance.
Okay, and reinforcement learning. How do you distill a policy?
In RL, you might have a complex, sample-inefficient agent that learned a good policy through lots of trial and error. You can then use distillation to train a smaller, faster student agent to mimic the teacher's policy, which actions it takes in which states, or its value function, how good it thinks certain states are. It's closely related to imitation learning.
So teaching a simpler agent by having it watch the expert.
Pretty much. It's also used in multi-agent RL, maybe to transfer successful collaborative strategies from a team of complex agents to simpler ones.
Fascinating. And you mentioned intersections, like autonomous driving.
Right. Autonomous systems often need to fuse data from cameras, LiDAR, radar, etc. Distillation can help create efficient sensor fusion models. You could potentially distill knowledge from a model trained with high-end sensors to one that uses cheaper, lower-resolution sensors, making the tech more accessible.
Okay, this is incredibly versatile. Let's get really practical now. If someone wants to do this, what tools are out there?
The good news is the main frameworks have great support. PyTorch has libraries like Torch Distill that bundle common distillation recipes, losses, and models. But you can also easily implement custom distillation loops using standard PyTorch components.
And TensorFlow.
Same story. TensorFlow and Keras have the Model Optimization Toolkit, which includes tools for compression, pruning, and quantization techniques often used alongside or integrated with distillation. Defining custom training steps and losses for distillation is straightforward there too.
Are there tools specifically for deployment, getting it onto devices?
Yeah, that's where things like ONNX runtime come in. ONNX is a standard format, and the runtime optimizes models for inference across different hardware. Intel's OpenVino toolkit is another key one, especially for optimizing performance on Intel hardware CPUs, integrated GPUs, specialized accelerators.
So when you're actually coding this up, what are the key things to get right? Best practices.
Setting up the teacher and student models needs care, thinking about architecture compatibility, maybe initialization strategies. The loss function details are critical. Choosing the right temperature, finding a good alpha value for balancing the losses, picking an appropriate learning rate, and maybe a schedule.
And the data.
Consistency in data pre-processing between teacher and student is vital. Using data augmentation during student training usually helps generalization. Batch size and normalization techniques also matter. It often requires careful experimentation and tuning.
How do you know if it's working? What metrics matter most?
You need a multifaceted evaluation. Standard accuracy or task-specific metrics like BLEU for translation, MEP for detection are baseline. But for distillation, you must measure inference speed, latency, and model size, memory footprint, compression ratio. You're looking for the best trade-off. Using proper validation and test sets is crucial.
And once you have a good distilled model, what about getting it out there? Deployment considerations.
Depends on the target. For cloud serving, you need scalable infrastructure. For edge or mobile, you use frameworks like TensorFlow Lite, PyTorch Mobile, CoreML. You often apply post-training quantization then to further shrink the model and speed it up, taking advantage of hardware acceleration if available.
What typically goes wrong? Common troubleshooting tips.
Overfitting the student is common, especially if it's much smaller or data is limited. Regularization, maybe more sophisticated distillation losses, or careful hyperparameter tuning can help. Sometimes the student just fails to learn effectively. You might need to check layer alignments, loss calculations, or learning rates. Using tools like TensorBoard to visualize training curves and activations is invaluable for debugging. Don't be afraid to iterate.
This has been incredibly thorough. So wrapping up the core idea, knowledge distillation is this powerful technique for making AI leaner and meaner, essentially.
Exactly. It lets us take state-of-the-art AI and make it practical. Run it on phones and cars, on small sensors, faster, cheaper, more energy efficient.
And it's clearly not a static field. It's constantly evolving with lots of exciting research still happening.
Absolutely. From self-distillation to cross-modal applications to making the process more automated, there's still tons of innovation happening. It's fundamental to deploying AI sustainably and widely.
Okay, a final thought for our listeners then. As AI weaves itself more and more into our lives, how critical will techniques like knowledge distillation be for ensuring this technology is not only powerful, but also accessible and sustainable in the long run? Something to ponder. Thanks for joining us on The Deep Dive.